This is Newton's law of cooling. It says the heat carried away by a moving fluid equals H times the surface area times the temperature difference. 3 of those you can measure with a ruler and a thermometer. But this one letter, H, the convective heat transfer coefficient, has haunted engineers for 2 centuries. Hidden inside it are the fluid's viscosity, its conductivity, its density and speed, the shape of the surface, and whether the flow is smooth or turbulent. So how do we actually find H? Not look it up in a table, find it. Let's build it up from the physics, step by step. Q equals H at delta T is easy arithmetic. All the difficulty of convection is packed into that single coefficient. Here is why. Density decides how much mass the stream carries. Viscosity decides whether the flow stays smooth or breaks into turbulence. Conductivity governs how heat crosses the thin film of still fluid against the wall. Specific heat sets how much each kilogram can soak up. Velocity thins the insulating layer at the surface. And the size of the object sets the scale of the whole thing. The catch is that these are not independent knobs. They are locked together through the Navier-Stokes and energy equations. That coupling is why there is no single clean formula for H. So we turn to a method that works every time. Before the recipe, one picture that makes everything click: the boundary layer. Right at the wall the fluid is stuck, it cannot slip, so its speed is 0. That motionless film can only pass heat by conduction, just like a solid. A little further out the fluid is moving in sweeping heat away. The temperature bends across this thin layer. All of convection lives in that bend. Because heat enters the fluid by conduction at the wall, H is really the steepness of that temperature curve at the surface, scaled by the fluid's own conductivity. Steeper curve, bigger H. That is the honest physical meaning of the coefficient. One more subtlety that trips people up. The fluid properties change with temperature, so which temperature do we use? For flow over an outside surface, we read every property at the film temperature, the average of the wall and the free stream. Hold on to that. It will differ for flow inside a pipe, and we will see exactly why. Here is the method. It never changes. Only the numbers you plug in do. 3 steps. Step 1, the Reynolds number, inertia divided by viscosity. It tells you whether the flow is orderly and laminar, or churning and turbulent. The threshold depends on the geometry. Step 2, choose the experimental correlation that fits your geometry and regime. It hands you the Nusselt number, the dimensionless coefficient, and rearranging gives H equals nu times K over the length. Step 3, put H back into Newton's law of cooling and read off the heat rate. Now watch the same 3 steps run on 2 very different problems. Case A, air at 20 degrees blowing at 3 meters per second over a half-meter solar collector plate sitting at 60 degrees, here in the Kathmandu Valley where the pressure is only 86 kilopascals. External flow, so properties come from the film temperature. The average of 60 and 20 is 40 degrees. And because Kathmandu sits at reduced pressure, the air is thinner, density drops to about 0.96, and the kinematic viscosity rises to match. That altitude correction is the whole reason we do this locally. Step 1. The Reynolds number works out to 75,000. For a flat plate the switch to turbulence happens near 500,000, so we are comfortably laminar. Step 2. Laminar flow over a plate has its own correlation. Nusselt equals 0.664 times the square root of Reynolds times the cube root of Prandtl. That gives a Nusselt number of about 162, and dividing by the length gives H of roughly 9 watts per square meter per Kelvin. Remember that number. Step 3. Newton's law of cooling over the quarter square meter plate gives about 88 watts carried off by the breeze. And the payoff for doing it locally, had we used sea level air, H would have come out 8 to 9% too high. Small, but it is exactly the kind of error that compounds when you size a real collector. Case A, air. Case B, same method, completely different setting. Water flows through a heated pipe, mean temperature 50 degrees, speed 1.2 meters per second, tube diameter 25 millimeters, wall held at 80. Here is the key difference from case A. Inside a pipe there is no faraway free stream to average against, the fluid fills the whole cross-section. So we read properties at the bulk mean temperature instead of a film temperature. For water at 50 degrees the Prandtl number is about 3.6, far higher than air's 0.7. Step 1. Same Reynolds formula, but now with the pipe diameter as the length. It comes out at 54,000. For pipe flow the turbulent threshold is only about 4,000, so this flow is firmly turbulent, a different regime, which means a different correlation. Step 2. Turbulent pipe flow uses the Didiso-Boelter correlation, Nusselt equals 0.023, Reynolds to the 0.8, Prandtl to the 0.4. That gives a Nusselt number of about 234, and dividing by the diameter gives H of roughly 6,000 watts per square meter per Kelvin. Step 3. The heated wall area is the pipe's inner surface, about 0.16 square meters, and the driving difference is 80-50. Newton's law gives roughly 28,000 watts, 28 kilowatts through one short section of pipe. Put the two cases beside each other and the lesson is obvious. The method never changed. Everything you plug into it did. Where you read the properties changed, film temperature outside, bulk mean inside. The regime changed from laminar to turbulent, and with it the Reynolds threshold and the correlation. Even the Prandtl number jumped from 0.7 for air to 3.6 for water. And look at the coefficient itself, about 9 for air, 6,000 for water. Nearly 1,000 times larger. That single ratio is why water cooling beats air cooling, why your car has a radiator and not just a fan, and we got it from the very same 3 steps. Put the entire method on a single card. Find the regime with the Reynolds number. Pick the correlation that gives you Nusselt. Solve for the coefficient H. Then apply Newton's law of cooling. Air in the open or water in a pipe, the path is identical. So H was never a number to memorize. It is the answer to 3 questions: how is the fluid flowing, which correlation fits, and what does that make the Nusselt number? Answer those, and convection stops being a black box. So, the